Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for their support for this series. So in our last webinar unit, we talked about SRS synthesis for wavelets, and now we're going to cover SRS synthesis for damped sinusoids. So I've already done a recording of the first half of this unit for the wavelets, so let's skip down to the damped sinusoids section. Okay, and here we are. So our goal in this case is to synthesize an acceleration time history to simulate a pyrotechnic shock for numerical analysis. Now that word simulate there I probably should have put in quotation marks. What typically happens is we'll go and measure field data, maybe from a stage separation test or have some flight accelerometer data, and we'll calculate an SRS from acceleration time history, or maybe we'll take several and make an overall envelope. But anyways, we do end up enveloping our measurements, and then we add margin on top of that. So the specification that we actually take into the test lab is much more conservative than the SRS from our actual measurement. But anyways, the goal here is to come up with a plausible time history that matches that SRS, and then that time history could be used, say, for a base input for a modal transient finite element analysis. So we're going to synthesize a series of damped sinusoids to satisfy the SRS. It's almost a tongue twister there. And an individual damped sine has the form shown here. So we have W sub n. This will be the acceleration for a particular damped sine function. Then we have the amplitude. Then we have the exponential decay, or the envelope of the signal, is shown by this term here. So we have the damping ratio, and then a frequency, and then we have the time minus the delay time, and here we have the sinusoidal oscillating function, which is damped by the exponential function. So what we're going to do is take a series of these damped sinusoids and mix and match them together so that we can satisfy the SRS. Now, when we were doing this for wavelets, we were also trying to optimize the waveform by minimizing displacement, acceleration, and velocity. And in this case, we're not going to try and do any optimization. We're just trying to match the SRS specification. So here's an example of a damped sine. This one has a natural frequency of 1600 hertz, and I'm calling it a natural frequency, but we could just abbreviate that as a frequency. And it has a damping ratio of equivalent to 3.8% damping. So you see acceleration g versus time in seconds. And you can clearly see the damping effect, the exponential decay effect going on as well. Now, here's a typical SRS specification. And this could be maybe for the case of a component mounted in the far field relative to say a linear shaped charge or frangible joint source shock. Or it could represent a component that's closer to the separation plane, but where the separation device is something more benign, or I should say less severe, say like a clamp band with bolt cutters, or a V-band with bolt cutters. And typically these SRS specifications will start at 100 hertz and go to 10,000 hertz. There obviously could be some variation, but this is probably the most typical pattern. For our purposes, though, we do need to concern ourselves with the fact that below 100 hertz the shock is uncontrolled. Now, in reality, what we expect below 100 hertz is a 6 to 12 dB per octave slope. That's what we expect. If it was 6 dB per octave, that would be a constant velocity line. If it was 12 dB per octave, it would be a constant displacement line. Of course, it could be intermediate value as well. So we're going to kind of use some engineering judgment and say that since we're going to do a numerical simulation, we do need to concern ourselves below 100 hertz. Now, this would be particularly the case if our component that's maybe we're doing a finite element model for has its natural frequency below 100 hertz. That would definitely be a concern. On the other hand, if our component has a natural frequency of 200 hertz or higher, then we would probably have very little need to be interested below 100 hertz. But in this case, let's say that we want to be a little extra cautious and we want to go down to, say, 20 hertz, just for an example. So what we're going to do is say, okay, we're just going to stick with this ramp. Now, in the case of this table, we can just by inspection say, oh, at 20 hertz, we're going to have 20 Gs if we have a consistent ramp. That's just by inspection because we have some very neat and tidy numbers there, which, by the way, are working out to 6 dB per octave. But if we had a little more complicated case with some kind of odd numbers, we could go to the vibration data GUI package. And we could go to, let's see, we've got dB octave calculations for log-log plots, separate frequencies. And we could say, okay, let's do SRS, okay. Let's find a new coordinate given 2 coordinates. So now this example here is kind of a trivial one since we can just tell by example what the resulting G level is going to be at 20 hertz. But I'll go ahead and do this anyways just to show you how this works. Okay, so we see that we have a 6 dB per octave slope, which is a constant velocity line, and in fact at 20 hertz we have 20 Gs. So that's how you can do that slope extrapolation. Okay, so the next thing we're going to do is we're going to set this up for a synthesis, for a damped sinusoid synthesis. And got quite a bit to explain to you. So let's go to our, well, what we need to do, let's back up. Let me back up a bit. We have to get those coordinates. There's 2 choices we have, or at least 2. We could take these coordinates and put them into, say, a Word or WordPad or some kind of ASCII text file and save that and then call that into MATLAB. Or another way is we can just, copy and paste. Okay, copy, Control V, paste, and I can put that spec into the MATLAB workspace. So there's the spec in the MATLAB workspace. Now I'm going to go to shock response spectrum, acceleration, and we have damped sine synthesis. Okay, so from some previous work I was doing, I already have some of the numbers set up here. I guess that's okay. So let's go ahead and read that spec, that SRS spec table in. And we're going to have English units, Q is equal to 10. Now, number of trials, probably should have at least 200. If I was doing this in earnest for some actual work problem, I might put some 400, 500, some higher number, some number of trials much higher than 200, but for now I'm just going to put in 300. The sample rate, now the sample rate should be at least 10 times greater than the maximum SRS frequency. So back in this table, the maximum SRS frequency is 10,000 hertz. So the sample rate should be at least 100,000 samples per second. Duration, this gets a little bit tricky. Now, we're going to take 20 hertz as our lowest. 20 hertz will be our lowest natural frequency. So then if we take the period of one cycle at 20 hertz, that's equal to 50 milliseconds. So let's say I want to have 3 cycles in at the lowest SRS frequency. So that would work out to be 0.15 seconds. Okay, and that's something we can play around with a little bit. Waveform reconstruction. I'm going to talk to you about this in a few minutes, but let's go ahead and take the default numbers for now. 5,000 trials per frequency, numbers of frequency 500. And of course, I encourage you to do this as a homework exercise, or maybe have your own SRS table. And some of these parameters you could vary just for experimentation, or to make it more suitable to whatever your particular specification is. Now, at this point, normally, I would click the at this point, normally, I would click the calculate button, which isn't showing up. So where did our calculate button go? And I think I need to restart this. So sometimes glitches happen, and I'm not bashful about making mistakes, because we can learn from our mistakes. Okay, so here is our SRS spec, and in a roundabout way, what I am telling you is I think I need to go back and make this software routine a little more user-friendly. Okay. Okay, now our calculate button shows up. So again, I need to go back and make this a little more user-friendly. And so at this point, normally I click on the calculate button. Now, in this case, for this particular spec and duration and sample rate and so on, this is going to take about 15 to 20 minutes to run, and I don't think that would be time well spent just watching numbers scroll by. So I've actually already done this, and I have an acceleration time history, and I'm going to show it to you via the PowerPoint slides. But please go back and do this exercise yourself, or use your own SRS spec. Okay, so just pretend I've hit the calculate button and the numbers are scrolling by in the MATLAB command window. I guess this is kind of like those cooking shows where they get some dish started and then they have to say, well, we already cooked it ahead of time, so here's what it looks like. Okay, so here's the setup. So you can do this exact case if you like for your homework, or vary the parameters, or input your own SRS spec, however you want to do that. And one of the neat things about this is similar to the case for wavelets, is that you could then save the resulting acceleration time history, velocity time history, displacement time history, SRS, and wavelet table. There is a wavelet table associated with this. I'll explain that in a minute. And then you can also export the acceleration time history to a NASTran format. And then that's useful. You could call that NASTran file into FEMAP, for example, if you use that as your preprocessor. Or you could just bundle the file together in the case control deck for your NASTran run. Okay, but let's go ahead and show you. Okay, before I show the results, here's the all-important steps. So we're going to generate a random values for the following for each damped sinusoid. That's the amplitude, damping ratio, and delay. Those are the three parameters needed to define a damped sinusoid. And we're going to take the natural frequencies in 1/12 octave steps. So we're going to do this for a family of natural frequencies in step 1, and then we're going to synthesize an acceleration time history for the composite. And step 3, we are going to calculate the SRS of the synthesis. Now, the first time through, we don't expect the SRS to really match up very good with the spec, so we're going to have to do a couple other steps here. So in step 4, we're going to compare the resulting SRS from the synthesis to the specification SRS, and then we're going to form a scale factor for each of the natural frequencies. Then we're going to scale the amplitudes of the damped sinusoid components accordingly. So what we're trying to do is to take this table and rescale the amplitudes to make this table the corresponding, which is the source for the composite time history, to be the best that it can be. So step 6, we generate a revised acceleration time history. And that series of scaling steps from steps 3 to 6, we repeat those as an inner loop for so many times or until the SRS error diverges. And then we repeat steps 1 through 7 as the outer loop. So we're going to come up with, in this case, for this example, 300 candidate waveforms, where a waveform is a series of damped sinusoids. And then we're going to choose the waveform. The winning waveform is going to be the one which meets the SRS specification with the least error. So that's how we're going to get a damped sinusoid series to match the SRS within reasonable tolerance bands. Now, if we were to just stop at step 9, here's what most likely would happen. Now, if we take that acceleration time history and integrate it to velocity, most likely there's going to be a baseline shift. And that's due in part to the fact that the initial velocity is unknown or uncontrolled. And if we double integrate to displacement, we get a ski slope effect. So we have some ridiculously high displacement at the end of our duration, whatever ending duration that we choose. And what we're really interested in when we do this type of base input type analysis, we're not interested in the absolute displacement. What we're really interested in is the relative displacement between 2 points or between 2 degrees of freedom. And it's that relative displacement that becomes important because strain is proportional to relative displacement. And then stress is proportional to strain. So for our stress analysis, we want to know what the relative displacement is. So think to yourself, you've got 2 points, and each of those 2 points on that component have these very high absolute displacements due to that ski slope effect. So you might think to yourself, okay, well, they both have the same ski slope effect, so if I subtract the absolute displacement at point A from the absolute displacement at point B, that will give me the correct relative displacement, and I don't even need to worry that there was a ski slope effect. That just all comes out in the wash. So what's the problem? Well, here I'll tell you what the problem is. That absolute displacement due to ski slope may be up to 2,000 inches. And the true relative displacement between those 2 points might be 1/1000th of an inch. So what happens is, due to significant digits and truncations and whatever, is that if we have a very high absolute displacement, we could have some, I'll call it numerical instability, for lack of a better term, that really makes an accurate relative displacement calculation difficult. So what we want to do is, as part of this process, and this comes into play with step 9, is we want to come up with an acceleration time history that, well, of course, we want it to simulate, I put simulate in quotation marks, a actual pyrotechnic shock event. We want it to satisfy the SRS, but we also want its corresponding velocity and displacements to each have reasonable values, stable values, and preferably with net zero displacement, net zero velocity. So how can we get stable velocity and displacement values? Well, I'm sure there's some method where we could take that synthesized acceleration time history from step 9, and we could do some integrations and trend removals, and then differentiate back, back on up from displacement to velocity to acceleration. And my phone's just ringing here. Okay, I'll have to leave a message. So that method is actually a pretty good method, and we use it when we do the, if you remember, the power spectral density synthesis that we've covered in a previous unit. We've done that method, and we were able to get a nice set of consistent displacement, velocity, and acceleration, where each of those three signals oscillate about the zero baseline. And that's all well and good. Well, for shock, I just decided to be a little bit clever, probably more clever than I should have been. And we're going to do something that's it's going to turn this into a bit of a Rube Goldberg process. But I thought to myself, we could take that damped sinusoid series and we could model it as a series of wavelets. And if we model it as a series of wavelets, then the net velocities and net displacements and net acceleration values will all be zero. It'll be a very good stable waveform. So the whole idea of wavelet or waveform reconstruction is probably something we should cover in a completely separate webinar unit. But I just wanted to let you know that's what's going on in Table 10. We're going to come up with a series of wavelets and subtract them from the series of damped sinusoids and try to minimize the error. And that's what some of those other parameters were all about in that synthesis example that I showed you a few slides ago. So after all is said and done and maybe 20 minutes have gone by, we come up with an acceleration time history as shown here. So as we look at this, and with some little bit of artistic license, I guess, this could represent a far field or maybe even a midfield pyrotechnic shock event. It's plausible. Now there's no exact criteria saying, oh yes, that does represent a pyro shock or not, but just sort of in a broad ballpark sense, yes, that does look like a pyrotechnic shock for far field or midfield. And here's the corresponding velocity. The corresponding velocity is stable, and it ends at zero. A bit of an oscillation about the zero baseline. Displacements can sometimes be a bit one-sided. This one almost looks like an N wave, like for an aerodynamic shock pressure. In other words, a sonic boom. That's just by coincidence. But this is a stable displacement. It's less than 0.3 of an inch, and it has a net value of zero. So that's a pretty good looking displacement time history there. So now what we have is we have a consistent set. We have acceleration as velocity and displacement, and this indicates that the acceleration time history would be suitable for, say, to base drive a structural dynamics model as part of a finite element analysis. And of course we also need to check the SRS specification. So here we have SRS, Q is equal to 10, that's as indicated on the title. Peak acceleration in G along the y-axis, natural frequency in hertz along the x. Then we have the three black lines. The middle black line is our nominal specification. We have plus and minus 3 dB tolerance bands, and the positive and negative curves are within those tolerance bands. So that's all looking good. And we're kind of sort of assuming here that our natural frequency of our structure is going to be 40 hertz or higher. Now, we could go and take the SRS of our signal and see what it is below 10 hertz, and we'd probably see that it starts to fall off with maybe about a 12 dB per octave. So there is energy down there in terms of response anyways. There would be response energy below 20 hertz. But for 40 hertz or higher, we're good to go with this. So let's do one other little exercise. This is something we always like to do. Here's our famous spring mass system. And in case you're getting kind of bored or tired with these, in our next webinar unit, we're going to start to get into multi-degree of freedom systems. But here we are again with our spring mass system subjected to base excitation. And by now you should know the routine with free body diagrams and Newton's laws and second order second order governing equation of motion and all that, and convolution integrals, and David O. Smallwood ramp invariant digital recursive filtering relationship. Let's see what happens at 600 hertz, Q is equal to 10. So we have our time history here, and we have single degree of freedom response to base input. And we have the file that's already acceleration. I already saved it, and I already have the numbers in here. So let's just do the calculation. And when we calculate a response, the peak response is about 640 Gs, of course. Well, actually, that's the relative displacement that you're seeing there. And then here's the acceleration time history response, going up to about 640 G. So acceleration response, relative displacement response. And then I also have the same plots in the slides here. So we have this is what we just did. So this is the acceleration time history and the corresponding relative displacement time history. And just as a reminder, there's also ways we can calculate. Okay, I need to fix this slide here. So I actually redid this example. We come up with different numbers, I think. So we had 640 Gs and 17 thousandths of an inch. Quick little on-the-fly changes here. Apologize for this, but okay, so if we take our peak acceleration at our natural frequency, which is 600 hertz, so we take 640 Gs, and then we take this scale factor, divide by 2 pi times natural frequency, which is 600 hertz, and then this term is squared, and that equals to 17 thousandths of an inch, which is the relative displacement. And that corresponds to, okay, it looks like it's on the negative side. We get the peak absolute 17 thousandths of an inch relative displacement. Maybe one more last thing before we go today. Let's go ahead and see what happened below 20 hertz. So let me go to vibration data, and let's go to shock response spectrum. No, let's go to time history, and we're going to apply that acceleration file from their synthesis to the SRS. So here's our SRS calculation, shock response spectrum. So we've run this one before, so I'm going to type in acceleration. And let's go from 10 to 10,000 hertz. Calculate the SRS for our synthesized acceleration time history. And we get a bunch of plots. We get our pseudo velocity, and here's our tripartite plot. Okay, here's the one I want to look at right now. So here's our specification. Well, actually our specification began at 100 hertz, but then we extrapolated down to 20 hertz for our synthesis process or synthesis run. And then below 20 hertz, the response drops off. That's probably about 12 dB per octave. But as long as our natural frequency of our component is I'm using 40 hertz because that's 1 octave above 20 hertz. So as long as we have 40 hertz or higher, we're probably not worried about that energy, that response energy down there. But on the other hand, sometimes we might have an isolated component, and our component might be isolated to 20 to 30 hertz. And in that case, we'd have to be a little more careful, and we probably in that case should extrapolate our spec down to 10 hertz, which would be, for this case, 10 hertz, 10 Gs. So that would have been a little bit better choice, but again, it just kind of depends on what the natural frequency is. So I hope you've enjoyed this, well, I said process. It is a process we went through today. Just a couple other notes, and we'll be talking about this in future webinars. There are ways within SRS finite element packages, or I should say there are ways within finite element packages to directly input an SRS and calculate the response. And that uses some approximation techniques we'll talk about later. There's a Naval Research Laboratory method is just one example. But my preference, just for my own idiosyncrasies or quirks, is I like to do a modal transient with an actual time domain signal. And someone could come along and argue, well, this time history that we synthesized is not unique. Well, that's true. So if you're concerned about uniqueness and all that, or lack of uniqueness, then then it might be possible or advisable to say synthesize 3 different base input time histories and then do 3 separate modal transient analysis and see how the results vary. And I'm suspecting that the results will not vary that much. So in many cases, I think you're good to go with just one run, but I'll leave that up to your engineering judgment. So if you have any questions, please send me an email, and have a good day. So thank you, and goodbye for now.